Hello, and welcome to the Atoms and Periodic Table video. So let's talk a little bit about atoms. So atoms are going to be composed of three different types of particles. So we have protons. Protons have a positive charge. Their mass is around 1 atomic mass unit. We'll talk more about these atomic mass units later, but they're essentially just a unit of mass that scientists devised to be about the right size to deal with atoms and molecules and really, really tiny stuff like that. So where are the protons located? They are in the nucleus or in the center of the atom. Along with them we have neutrons. Neutrons have zero charge. Their mass is virtually identical to that of the proton, also around 1 atomic mass unit. And they are also located in the nucleus. Finally, atoms are composed of electrons. They have a -1 charge. Actually, I should draw attention to the symbol right here. We're going to use this E- symbol sometimes in chemistry classes because we talk about electrons a lot. Electrons are incredibly important when it comes to chemistry. The mass of an electron is very small. It's about 1,800 times smaller than that of a proton or neutron, so they're very, very light in comparison. And they're located outside the nucleus. They sort of swarm around the nucleus in some fairly randomish patterns. There is some pattern to them, but their motions are very unpredictable. So moving on, there's a number of vocab terms we're going to need in this chapter, and one that's very important is what's known as atomic number. So atomic number is listed above the element on the periodic table. So if you look, there's usually a symbol, and there's like a integer number above that symbol. That number above the symbol is the atomic number. And so the atomic number indicates the number of protons in an atom, and it's also essentially kind of the identity for an element. So right here, sodium, for instance, has 11 protons, and what that means is that any atom with 11 protons is going to be considered to be sodium. If we have more or less protons, well, that'd be a different element entirely. So, for example, hydrogen has atomic number of 1, which means every atom of hydrogen has to have 1 proton. If we have more than 1 proton, it'd be a different atom. Similarly, carbon has atomic number of 6. That means that every single atom of carbon must have 6 protons. If it has more or less, it's a different atom. And you guys are pretty sharp, so I'm sure you're getting the trend by now. So the number of electrons is going to be actually equal to the number of protons when you see that word atom. So that term atom means that we're electrically neutral. In other words, our protons have to equal our electrons in order for that term atom to be used, because it means that we're neutral. And so that means the atomic number for an atom will also be the number of electrons. So aluminum, for instance, is atomic number 13, which means we have 13 protons, but the atom of aluminum is also going to have 13 electrons, and that positive charge and negative charge actually cancels out to an overall or a net charge of 0 for any atom. So again, atomic number will also equal the number of electrons in addition to the number of protons when it comes to atoms. So it's tricky in this chapter because we have a number of similar terms. We're talking about atomic number. Now we're going to move on to what's known as the mass number. And so the mass number is going to equal the number of particles in the nucleus, or in other words, our protons plus our neutrons. And so we call this the mass number because the protons and neutrons are like the heavy things in the atom. So they are what are responsible for most of the mass of the atom. So what do atoms look like? Well, these aren't really to scale. Electrons actually roam over a very, very wide distance, but essentially we have, in lithium right here, atomic number 3. So we have 3 protons, I've marked those with dots, and we have 3 electrons. But this particular one also has 4 neutrons, so our mass number here would actually be 7 for this lithium. And over here we have carbon. Carbon's number 6. And so that means that we would have 6 protons, and we'd also have 6 electrons in this atom. So please pause the video and complete questions 1 and 2, but hold off on question 2C for now. Welcome back. Let's look at some examples. So if an atom of zinc has mass number of 65, how many protons in a zinc atom? Well, we'd have to whip out a periodic table, and we'll be using a lot of periodic tables this quarter. You'll actually be given periodic tables for all the exams and such. And so zinc is, it is atomic number 30, meaning we have 30 protons in a zinc atom. Then we're asked how many neutrons would be in that zinc atom. Well, we'd have to have 35. And how do we know? Well, if our mass number is 65, 30 plus 35 totals that 65. Because again, protons plus neutrons give us that mass number. And then what is the mass number of a zinc atom that contains 37 neutrons? So the neutrons can actually vary from atom to atom. This one actually has more neutrons than in the previous question. And so that means our mass number here would now be 67, because it's going to be our protons plus our neutrons. Because zinc will always have 30 protons. If it has more or less, it's a different element, but we can have differing numbers of neutrons. So we can have zinc with mass number 65, or we can have zinc with mass number 67. So let's see how we did. Bam! We did great. We aced this. So let's talk about this idea of varying number of neutrons. There's a name for this, and this name is isotopes. So the term isotopes is used to describe when we have the same element with differing mass numbers. In other words, we're going to have the same number of protons, because the identity of the element, the same element means we have the same number of protons, but we have a different number of neutrons. And so one way we can distinguish this is what's known as the atomic symbol. And so we write the symbol for the element, and then we put our atomic number to the lower left and our mass number to the upper left, excuse me. And so for this particular element right here, it's magnesium, that's atomic number 12. That means we have 12 protons. And we'd actually also have 12 neutrons, because we'd need another 12 particles to add up to that mass number of 24. And so isotopes are going to have virtually identical properties, both chemically and physically, except the one with more neutrons is going to have a greater mass, because there's more stuff in there, more matter in there. And because it has a greater mass, it's also going to have a greater density. But otherwise, they're pretty similar, other than radiation. But don't worry about that for now. We'll talk about radiation way later in the quarter. So go ahead and pause the video, and please complete questions 3 through 5. All right, welcome back. Now let's talk about the periodic table. So the periodic table is broken down into columns and rows. And so the columns are referred to as groups. And the groups are very important because the elements within a group actually have similar properties to each other. That's how the periodic table is actually discovered and crafted, is by seeing these elements with repeating properties. And then the rows are referred to as periods. So the columns are groups, and the rows are periods, and we'll be talking a fair bit more about the groups. They're going to be important. They'll come up a lot actually in upcoming chapter. And so another way the periodic table is broken down is the location is different for where the metals, nonmetals, and metalloids are located. So the metals are marked in blue, and they sort of occupy the majority of the periodic table, the biggest section here. Bam, so there are our metals. I'll put a big M on there for metals. And then over here we have our nonmetals hiding on the upper right. But we do have another one lurking in sort of a surprising location. We have a nonmetal way over here. We have hydrogen. So the ones marked in yellow are nonmetals. And then in between we have our metalloids, or sometimes referred to as the semi-metallic elements. And so again, you can sort of tell what class of element something is based on periodic table location. But let's talk about the different properties for these different classes of elements. So metals have all the properties you associate with metals. They're shiny and ductile. So they're reflective, and ductile means that we can change their shape without them shattering. So like for instance, an aluminum can, if you bend it, it dents, it doesn't shatter. Same thing with your car. If you bump into something, it dents rather than shattering. And they're good conductors of heat and electricity, which is why we make wires out of them and pans out of them and things like that. So nonmetals actually have all the opposite properties of the metals. They're generally not very shiny if they happen to be solid, and they're generally not very ductile or malleable, so that means that they're going to be brittle. So if they're solids, usually the nonmetals are going to be brittle and not very shiny. A lot of these are gases though. And then we also have them as poor conductors of heat and electricity. So we could actually say they're good insulators would be accurate. And then we finally have the metalloids. The metalloids are better conductors than nonmetals, but not as good as metals. So what does that mean? Well, we tend to use them as semiconductors. So like silicon, for example, is a type of metalloid. So please pause the video and complete question number 6. All right, welcome back. We are almost done. Let's go ahead and finish out the chapter. The last topic we're going to deal with is what's known as atomic mass. And so be careful, because again, we have all these similar terms: atomic number, mass number, and atomic mass. So that's what the meme to the lower right is saying, is look out, because they have all these similar names. So we want to figure out the atomic mass of chlorine, and we're going to look at the differing isotopes. So in nature, all elements occur as a mix of isotopes. In nature, chlorine occurs primarily with mass number 35 and 37. So about 3/4 of chlorine in nature is this mass number 35, and about 1/4 is mass number 37. So how do we figure out the atomic mass? Well, the atomic mass is our average mass of the chlorine, figuring out looking at both the masses of those isotopes and their abundances. And so if we scoot on to the next page here, it shows how we do this calculation. So we take our mass, and this would be probably given in your problem, and we use the percentage, we turn it into a ratio over 100, and we multiply these together. And we end up with 26.49 AMUs. We're going to do the same thing for our other isotope, take our mass and AMUs, then use the percentage. These would be given in the problem, multiply those together. We end up with our 8.962, and when we sum these together, we end up with 35.45 atomic mass units. The great thing about this type of problem is we can just check our answer on the periodic table. If you look below chlorine on the periodic table, you see 35.45. So one of the things you may be asked to do in this chapter is this type of calculation. And again, generally you'd be given the masses of the isotopes as well as their abundances. So the stuff in these columns would be given, and you'd have to solve for this value here. And the math would be just like what's shown. So congratulations, you made it through. Go ahead and end the video and complete question number 7. And if you have questions, I just want to remind you the discussion board's a great place to put them.